Just a few concepts regarding electric circuits. So in an electric circuit, you need to be able to draw a circuit. So a battery, we draw with a shorter line and a longer line. In South Africa, the convention is that the shorter line means the negative pole of the battery and the longer line means positive. It's not an international convention, but in South Africa, we use it like that. Okay, then a switch can be open or closed. Then a resistor, a light bulb, and then a voltmeter, which measures potential difference, and an ammeter, which measures current. Okay, so an ammeter measures current flow, and we always connect an ammeter in series. A voltmeter, we measure potential difference and potential difference. The voltmeter is always connected in parallel. Always. The function of a voltmeter is that a voltmeter has a very high resistance. So you have to put the voltmeter in parallel, otherwise it's going to stop the flow of charge. An ammeter has very low resistance, supposed to be 0, so it doesn't influence the current. So if you would put it in parallel, then you would short circuit the circuit. So an ammeter has to be connected in series, a voltmeter has to be connected in parallel. Right. Then the three main parts of any circuit is the potential difference, the current, and the resistance. Potential difference is measured in volts, and you have to distinguish between what's called the EMF, the electromotive force, and the terminal potential difference. So the difference there is that the EMF is the potential difference measured across a battery when no current is flowing through the circuit. So there's no current flowing through the circuit. So yeah, we would measure the potential difference across a battery when no current is flowing. So that means, in other words, that switch is going to be open, right? So when the switch is open, no current is flowing through the battery. And then what we measure across the battery is basically the full potential of the battery, the total amount of potential difference that the battery can deliver when no current is flowing. But the moment there is current flowing, then inside the battery, there is what we call internal resistance. And the internal resistance of the battery uses some of the total potential difference that the battery would have had. It uses inside the battery while the current is flowing through it. So therefore, when we measure what's called the terminal potential difference, then we still have the voltmeter across the battery, but now the current is flowing. So now that switch is going to be closed. So the switch is now closed, and now it's the potential difference across the battery when there is current flowing. Okay, so it's when the switch is closed. Okay, so the only difference between EMF and terminal potential difference is whether the current is flowing through it or not. Terminal potential difference will always be less than EMF because with terminal potential difference, the internal resistance of the battery decreased the total potential difference available to the circuit. Then calculating potential difference. Potential difference is the amount of work done per charge. So V is W over Q, where V is the potential difference in volts, W is the work done in joule, and Q is the charge, which we measure in Coulomb. So you remember charge, positive or negative charges, and in a real circuit, it's only really electrons that can move, not protons, not positive charges. Okay, so you could get a calculation where two of these three variables are given, and you just have to determine the third variable using this formula. Then current is the second thing that we always get in a circuit. So the current is the rate of the flow of the charge. So it's how many charges or electrons pass a certain point in a certain time. So in this circuit diagram, that would be there because that ammeter measures the current. So the amount of charge that passed this point in a certain time. Okay, so we measure current in amperes, and the formula we use to calculate current is I is equal to Q over T, where I is in the current, and current is measured in amperes. Q is the charge that is measured in Coulomb, and T is the time, which is measured in seconds. So if they give you time in minutes or hours, you need to convert into seconds. Then conventional current flow direction. We have conventional current versus real current. So conventional current is defined as the flow of positive charges from the positive part of the battery through the external circuit to the negative part of the battery. Okay. So in this diagram, conventional current flow would mean we have positive charges that flow from this positive side of the battery through the external circuit to the negative part of the battery. Okay. Now, real current, we said before, only electrons, only negative charges can move. So real current is actually the flow of negative charges, and they would flow then from the negative part of the battery through the external circuit to the positive part of the battery. So that's real current. So conventional current, the one we use in theory, is not actually the real current. So we actually work with it the opposite way around. But it doesn't matter. It makes it doesn't influence the calculations at all. So we just leave it like that because that's internationally the convention that is used. Then resistance. Any circuit has resistance. So resistance is measured in ohm, and we use this omega symbol for it. Resistance, the definition of it is it's the opposition to the flow of charge. So it opposes that charge that wants to move. Okay. Now, to increase the resistance, what we do to increase the resistance is we increase the length of the resistor. We decrease the thickness. So the thicker a certain resistor is, the lower its resistance. But the thinner it is, the higher the resistance. And then the type of material has a microscopic effect on it, because some material just have more. Well, basically what happens is you have what we call the valence band. Do you remember what the valence band is? It's the last energy level in which we find electrons. And then in order for electrons to flow, they need to move out of the valence band into the conduction band. So now what happens, that's conduction band. So in the conduction band, electrons are free to flow. So now if you have a material that has a high resistance, it means that the valence band and the conduction band are very close to each other. So while electrons are trying to flow here, the electrons in the valence band are in the way. Okay. So if it has lower resistance, there's more space for the electrons to actually move. Right. Then a battery runs flat because of its own internal resistance. So there's components inside the battery where the electrons need to move through, from the negative pole of the battery to the positive pole of the battery in conventional current, or the other way around in real current. And while the electrons need to move there inside the battery, there's things that it needs to move through. And as it moves through those things, it is those particles inside the battery oppose the flow of the charge. So that's internal resistance, and that internal resistance of the battery eventually makes it run flat. Maybe I should just add here that the problem here is actually that the electrons jump because of the heat. So you know that the higher the temperature, another thing here is we increase the temperature. So the higher the heat, the more these electrons out of the valence band jump basically in front of or in the way of the electrons in the conduction band. So actually, if it has a conduction band close to the valence band and it's at a low temperature, it has a lower resistance and it conducts electricity easier. It's just that as the temperature increases, it makes the electrons move more, because temperature is a measure of the kinetic energy of the electrons. So those electrons cause heat transfer. So there's a change in energy from electric energy into heat energy. And that electric energy that's converted into heat energy makes the battery eventually run flat. Okay, now how current, potential difference, and resistance acts in a series circuit is different than how each one of them acts and how we determine them in a parallel circuit. So in a series circuit, you remember, that means that all of the components are connected in such a way that there is no place for the current to split. So there's only one pathway for the current. It comes out of the battery, through that ammeter, through that resistor, that ammeter, that resistor, that ammeter, and back to the battery. No split in the pathway that the current can follow. So what you need to know about current is that current in a series circuit is exactly the same everywhere. Current in a series circuit stays constant throughout the whole circuit. No change. So what that means in this specific circuit is that ammeter reading 1 is going to be equal to ammeter reading 2 is going to be equal to ammeter reading 3. Okay, current is exactly the same everywhere. Then potential difference. So what you need to understand about potential difference is the words potential refers to the potential energy available to be converted from electric energy into other forms of energy. So whatever this resistor is, if this is a light bulb, it's going to convert electric energy into light energy. If this is a heater, it's going to convert electric energy into heat energy. If this is a fan, this resistor is going to convert electric energy into kinetic energy. So potential energy means the amount of electric energy available to be converted into other forms of energy by a resistor. Potential difference, the difference means we measure how much potential is left before that component and how much potential is left after the component. And then we measure the difference. And then we know by the difference how much this one used. So that's where potential difference comes from. So now that battery gives us a maximum amount of potential difference, potential. And that potential is used up, always used up in the circuit. So let's say, we have 5 volts given to the circuit by the terminal potential difference. That potential difference plus that potential difference is going to add up to that 5. So in a series circuit, if that's our potential difference, voltmeter reading 1, then voltmeter reading 1 plus voltmeter reading 2 is going to add up to that terminal potential difference. Okay, so you remember terminal means the potential difference across the battery, measured across the battery when current is flowing. Okay, so that's basically the EMF minus the potential difference lost, the potential lost by the internal resistance or used by the internal resistance. Okay, so if we put this in words, the potential difference, or let's say the sum of the potential difference across the different components add up to the sum of the potential difference across the different components add up to the terminal potential difference, which is most now always across the battery. Right. Then the resistance. To calculate resistance in series, we simply say the total resistance is equal to the resistor 1 plus resistor 2 plus resistor 3, however many resistors there are, we just add them. Okay, to get the total resistance. So that's how each one of these works in a series circuit. It works differently for parallel. Okay, so for a parallel circuit, if we have that's our parallel connection. So 3 resistors in parallel with voltmeter 1, voltmeter 2, voltmeter 3, ammeter 1, ammeter 2, ammeter 3. Then we have there also voltmeter 4. There we have ammeter 4. Okay. Now you can see here that ammeter 4 measures the total current, right? And terminal potential difference there measures the terminal difference across the the whole the battery. Okay, now with a current, the current here splits up. So here we still have the total current, A total, right? And now here, that current splits up. So some of the current goes through this resistor, some here and some there. And the amount of current that goes into each part of that parallel circuit is dependent on the resistance. And that dependence is inversely proportional. So what that means is that if we have a high resistance on this side and a low resistance on this side, then here where we have the low resistance, we will have the higher part of that total current flowing through there. And if we have a high resistance here, we'll have a low part of that total current there. So current in a parallel connection is inversely proportional to the resistance in that connection. So in other words, the current flow, the current through the part of the parallel connection with the highest resistance will have the lowest current flow. And that's now part of the total current because the current splits up. Yeah, where these three connections get back together, the current gets back together again. So current is inversely proportional to the resistance in a parallel connection. Okay. So in other words, a parallel connection acts as a current divider. Parallel connection acts as a current divider. Right. Now, potential difference. Remember that potential difference means the difference in the potential available for transfer, for energy transfer. Now, the amount of energy available here is the same as the amount of energy available there and there and there. Why? Because from there to there, from there to there, from there to there, all of those spaces, there's no resistor that could transfer any of that energy into other forms of energy. Now there, energy is transferred, there energy is transferred, and there energy is transferred. And now there we're going to have a difference. There we're going to have the same difference. And yeah, we're going to have the same difference. And now if you look at the amount of energy available there compared to the amount of energy available there, those will be the same, the same, the same. Why? Because there's no resistor that can use the available energy to transfer it into something else. So, what I'm trying to say is the difference in potential difference across the whole big parallel connection from there to there is going to be the same as each individual potential difference. And each individual potential difference, each individual connection in that parallel connection is going to have the same potential difference as all the others. Okay, this is important for you to take note. That potential difference there across the one connection is exactly equal to the potential difference across the other 2 or 3 or however many there are connections, parts of that parallel connection. And they are all equal to the parallel, the big connection across the whole parallel connection. That potential difference. Okay. So in a parallel connection, the whole connection's potential difference is equal to the potential difference of each individual one, and each individual one is equal to each other. So they are all equal to each other, not equal to the total of them. They are the same. This is important for you to take note. Then the resistance. Calculating the total resistance in a parallel connection, here we say 1 over that total parallel connection. That means parallel. You remember parallel, we indicate like that. 2 parallel lines with arrows. So the total parallel connection is equal to parallel 1 plus resistance in parallel connection 2 plus resistance in parallel connection 3. Now you need to remember, when you've added those, you're going to get an answer that is going to be 1 over R total. Now to get R total, you're going to have to swap those 2 around. Okay? So let's say, for example, you got your total there as that's equal to 3 over 4, then that means that your R total is going to be 4 over 3. So you need to remember to swap them around, okay, to get to your final answer for resistance. Okay, then if you have 2 resistors in parallel, so you have one on that side and one on this side, and this one is R1 and this one is R2, then the total resistance in that parallel connection is going to be the product of those 2 divided by the sum of those 2. So this is one formula you can use if you have only 2 resistors. Then you take the product of the 2 divided by the sum of the 2 to give you the parallel connections total resistance. Okay. So what you need to do is you need to make sure you understand the difference in how current, potential difference, and resistance acts in a parallel circuit and how each one of these acts in a series circuit. Then one last thing about the calculations of series or electric circuits is Ohm's law. In Ohm's law, we use the triangle vir V is equal to I times R. So if you need to calculate V is equal to I times R. If you need to calculate I, you close I and you're left with V over R. If you need to calculate R, you close up R and you're left with V over I. You see there, if we close up V, I times R is left. So that's I times R. Again, V is potential difference in volts. I is current in amperes. and R is resistance in ohm. Okay. So this is true for two things. For the total circuit, this is true. And this is also true for each individual component. So if you need to calculate potential difference of the battery, then the total potential difference is equal to the total current multiplied by the total resistance. If you need to find potential difference across component number 1, then the potential difference across component 1 is equal to the current through component 1 multiplied by the resistance of component 1. If you need to calculate the potential difference across a whole parallel connection, let's say parallel connection A, then that's going to be the current through the whole parallel connection A multiplied by the resistance of the whole parallel connection A. So this is true for each individual part of the circuit as well as for the total circuit. So when you need to do calculations, the only tricky thing is you just need to determine exactly what is the current in that part of the circuit I'm working with. Exactly what is the resistance in that part. What is the potential difference in that part.